Okay, welcome once more. Let's see what we're doing today. Looks like we're still in the aircraft instrument system class, so now we're up to calibrated gauges. Basically, that's a number of gauges where the calibration or the actual ranges are written on the dial face to correspond with the actual condition that's being measured. I like also the word condition gauges, what condition a number of items are, like how hot is it, how much pressure is there. Okay, either way, let's go ahead and get into it. First section will be temperature. Start out with the bimetallic thermometer. It's a very useful indicator in aviation. The temperature sensing element of a bimetallic thermometer is made of two dissimilar metal strips bound together. You can't really see it. Normally, the length of the needle, or in this case, the coil, one side is one material, and the other side of the coil is a different material. So they expand at different paces at a different rate when temperature changes. One end of the bimetallic strip is fixed, in this case in the middle, and the other end is coiled, and a pointer is attached to the coiled end. Alright, so it's not in the middle, it's actually fixed at this end, and the coiling takes place in the middle. And that part is set in the instrument housing. Oh, the needle is. When the bimetallic strip is heated, the two metals expand. Since their expansion rates differ and they are attached to each other, the effect is that the coiled end tries to uncoil as one metal expands faster than the other. This moves the pointer across the dial face of the instrument. And you can basically, once the needle is here, you can test the material directly with a known instrument to make sure, and if it reads, in this case, 25, you know that's where you would mark your, I can't see, the needle goes through it, it may be actually be, I think it is 25. But irregardless, that's where you would mark it, and you would adjust this outer line also. Another temperature that is read, or one of the common applications of a temperature indicating gauge, is the outside air temperature, OAT. The pilot will use that to calculate his true airspeed. As illustrated, the OAT gauge is usually mounted near the top of the windscreen or out the side window besides the pilot. And it's a normal thermometer that many people may have at home. Certainly it's aviation level. What's shown? A Piper has their own instrument. We could see aircraft in script letters. Looks like these days it would look like more of a collector's item than, but I'm sure it's still functional. And every so often you may have to check these for their accuracy. Ways of measuring the temperature, the heat, or versus the lack of heat. Often is this board-on tube, and it's the semicircle. It's hollow, Well, let's see what it says here. It's used as a direct reading, non-electric temperature gauge in simple light aircraft. Well, that's one nice thing to consider. It is non-electric. You don't see any wires going to it. Therefore, it's going to operate irregardless of your electrical condition. By calibrating the dial face of the Borden tube gauge with the temperature scale, it can indicate temperature. There you go, a real discussion of the calibration. The basis of operation is the consistent expansion of the vapor produced by a volatile liquid in an enclosed area. So it's not a gas inside the tube, inside the semicircle, the darker shaded portion of the component. This vapor pressure changes directly with temperature. So apparently the liquid would give you more of an effect than a gas would. The gas, it may actually change its pressure, but not enough to actually bend the tube, whereas the liquid can. By filling a sensing bulb with such a volatile liquid and connecting it to a Borden tube, the tube causes an indication of the rising and falling vapor pressure due to temperature change. In this type of gauge, the sensing bulb is placed in the area needed to have the temperature measured. A long capillary tube connects the bulb to the Borden tube in the instrument housing. So if you're going to measure, let's say, the cabin air pressure, you would put the temperature probe in the cabin, and the capillary tube runs from the probe to the instrument or indicator itself. Capillary tube, there's a definition if you haven't already read it. There's electrical temperature measuring indicators. We did see that there was no wires attached to the last one, to the Borden tubes, but there certainly is electrical based temperature measuring devices. They're widely used in many types of aircraft to measure carburetor, air, oil, free air, and more. They're also used to measure low and medium temperatures in the 70 degrees Celsius to 150 degrees Celsius range. So it's low and medium range temperature that you can use these type of devices. The resistance thermometer. The principal part of the electrical resistance thermometer are the indicating instrument, shown there in the black circle, the temperature sensitive element or bulb, shown in the red picture, and the connecting wires and plug connectors. The temperature sensitive resistor element is a length or winding made of nickel manganese wire or other suitable alloy in an insulating material, which is in effect a fancy wire. The resistor is protected by a closed-end metal tube attached to a threaded plug with a hexagonal head. And you can see the hexagonal head in the illustration. And there's even some holes for you to safety wire this type of thermocouple. And you will have to do a project like that, but it may not be until engine instruments, or you may be called on it in your oral and practical examination. Certainly practice your safety wiring on components that resemble this. We'll take a look at the details of one of these temperature bulbs or sensing elements. Of course, they're all a little different, but you can see that's an AN connector on the right side of it, and it's got two plugs that are in effect what is connected to the electrical system. A few gaskets, which, you know, gaskets have to be inspected. There's a compensating coil, a mica insulator. I mean, the main nuts and bolts of the whole component is this long heat conductor on the inside. And the little details is there's a nickel winding on a mica core, and the stem appears to be you know, the outside portion that is actually serving as the structure to the component. Probably a metal tube. Other type, well, there's a couple different types of electrical resistance temperature gauges. One is wound. The windings are in this Wheatstone bridge configuration. The resistance of R4, well, let's find R4. That would be the one off here to the right. R1 is a resistor on, I guess, the northeast side of the component. R2 is the resistor on the northwest. R3 is the resistor on the southeast. So what's the R4? Oh, R4 is over here. Okay, so basically, instead of having another resistor between A and, in effect, the ground here, they're actually substituting one of these thermometers. But you can kind of see from where the probes at the end of the line, the AN connector, you can see where they actually tie in. And basically what they're doing is they're going around in a circle. There's various resistances, and you can see the indicator is affected by, in effect, the magnetic field of the electrical forces that it's being faced with. Here's another indicator. In the middle they've got a calibrated resistance, so it's more of an adjustable or a variable resistor here in the middle. Okay. Should know at least the word Wheatstone bridge, and think of it as the square that's sitting on one of its corners, which is different than the ratiometer, which is basically the other main type. The ratiometer is more accurate than the Wheatstone bridge because it compares ratios which eliminate indicator errors due to small changes in source voltage. Alright, so I suppose the needle wouldn't jump around as much as it would here, because there's a ratio sharing. I'm having a little trouble with that word. What do we want to know about the ratiometer? That's, yeah, the ratiometer, so it must be ratios. I don't think that's the correct pronunciation, but we may look it up. You can see the core, and there's an electromagnet being formed at A and B, and depending on the difference in the resistance, the needle is attracted more to, if it tilts this way, it's going more to the south side, or tilts that way, it's more to the north side. So small changes could make a big difference. Right, ratiometer. You can see it's not exactly a Wheatstone bridge wiring. The bulb is actually tied in here, and the two probes of the bulbs go in the two different directions. Thermocouple temperature indicators. This is more for the high temperature. like it would have like exhaust gas temperature and cylinder head temperatures. And that's what I'm seeing in the text here, CHTs and EGTs. High temperatures, two applications are the cylinder head temperature in reciprocating engines and exhaust gas temperature, EGT, in turbine engines. They're made from a variety of metals, depending on the maximum temperature to which they are exposed. They're basically, probably you can pick from hundreds of them. Iron and constantan or copper and constantan are common for CHT measurement. Chromal and aluminal are more common for turbine EGT thermocouples. So I sometimes will use as a memory aid the exhaust gas, and I try to picture a chrome or aluminum, say tailpipe or something, just in my mind, just so I can get that chromal and aluminal, as opposed to copper or iron and constantan. You can see the actual electrical schematic for a thermocouple is quite basic. Voltage generated in a thermocouple system is proportional to the temperature difference on or between the two ends. So there's either no temperature here or no additional temperature, just ambient temperature, compared to the overheated condition here. That difference will measure in the thermocouple gauge, temperature gauge. And you can read this definition if you haven't already. There's a typical thermocouple there off to the side. Oh yeah, I said hundreds. See, here's an example of what a catalog might look like. The various codes. The circuit sensitivity to variations in resistance also requires that the wiring connected to the thermocouple be carefully matched to the system, especially when you're going to be measuring, well, either way, recips or turbine engines. But these thermocouple leads are color-coded for easy identification and come in matched pairs that are secured together by a common braid. They don't really quiz you to this extent, but it's interesting for you to know and maybe get a little better feel for thermocouples and their use. And it's certainly, fertile ground for further analysis. Some thermocouples are permanently attached to the leads, others are removable. A technician should always use the correct lead for the system and never change the length, since that would change the system's resistance. You would think that comes up a lot by the number of questions that they're going to ask you about that particular item, but just be aware that you're not to like shorten the leads or do anything foolish with the thermocouple connections. Turbine engine exhaust gas temperatures are measured by using, what's your little memory? What do you remember about exhaust gas? Was it iron constantan, chromal aluminal, or ratiometer electrical resistance? I think my little memory pneumatic of thinking of the exhaust pipe as being a chrome exhaust pipe gonna make me answer B. And over time, that's what you would end up picking. But early on, a lot of these words probably sound the same. It is chromal aluminal thermocouples that are used for turbine engine exhaust gas temperatures. That's very high temperature, as you can imagine. Certainly wouldn't want to put your hand on the exhaust of a turbine engine. An oral question might come up. What type of temperature sensing system is normally used to measure a turbine engine exhaust gas temperature? So they may ask you that. Certainly, you're thinking that's extremely high temperature. So probably some of these smaller ones like electrical resistance and Borden tube, that's just not going to measure up to these type of levels. So you might end up saying something in the thermocouple range. That may be enough. They may just want a couple words on that. Let's see. It is a thermocouple type system. Written question. Aircraft temperature thermocouple leads may A. Not be altered and are designed for a specific installation. Sounds good so far. B. Be installed with either lead to either post of the indicator. Or C. May be repaired using solderless connectors. All right, so B and C are big no-goes when it comes to playing with thermocouples. A is the best answer. Do not alter them. They're designed for a specific installation. Okay. Resistant types temperature indicators using the Wheatstone bridge or the ratiometer circuits may be used to indicate the temperatures of which of the following? The resistance type, and they do show the two types. That's a little low and medium temperatures is what you automatically should think about there. So you're in effect going to eliminate some of the high temperature items like, well, we already know exhaust gas temperature from the turbine engine. Anything else? Free air? No, that's not going to be a high temperature. Carburetor air? Same. Engine coolant? No, that's within normal limits. Oil temperature? Also not. Cylinder head temperature? Now you wouldn't want to put your hand on the cylinder. But you could probably dip your finger in the oil or the coolant near the carburetor air. I'm not certainly that's not. You probably wouldn't even be able to tell the difference. Same with free air. So certainly exhaust gas temperature and cylinder head temperature. So is that one of the options? 2 and 6? Okay, it must be a not. May be used to indicate of which of the following. All right, so it's everything except 2 and 6, which looks like that would be B. Apparently the cutoff is around 300 degrees Fahrenheit. So think about how hot your oven might get at 300 degrees Fahrenheit. Most of our cooking is done, what, at 350? But temperatures below that, while you're preheating your oven, they can be measured by an aircraft instrument resistance change instrument such as a Wheatstone bridge or the ratiometer. You don't have to use thermocouples for that type of application. All right, I think enough said about that. An oral question. What is the signal source in an electrical resistance type temperature indicating system? The signal source. All right, that's not necessarily the electrical source. Each one of those signals was actually attached to the probe. Yeah, you remember the Wheatstone bridge, the square that's sitting on its edge. One of the resistances was actually this temperature probe, and similar to the ratiometer. So we're going to say a temperature probe or bulb or sensing element. All right, pressure. It's another condition of the aircraft, usually of your environment or the engine's environment. So an aviation pressure is measured to a high degree. It's the basis of most of the early aviation instruments, and it still is a high percentage of the instrumentation on the aircraft. All right, here it looks like we're also using the Bourdon tube. A little bit different configuration of it, but apparently the Bourdon tube also works for pressure in addition to temperature. It's the internal mechanism for many pressure gauges used on aircraft. When high pressure needs to be measured, the tube is designed to be stiff. Gauges used to indicate lower pressures use a more flexible tube that uncoils and coils more readily. Okay, so basically it wouldn't be as hard to coil and uncoil. Ingenious. Most Bourdon tubes are made of brass, bronze, or copper. Alloys of these metals can be made to coil and uncoil the tube consistently numerous times, so it won't get work hardened where all of a sudden cracks are going to appear. A Bourdon tube is connected to a mechanical linkage in order to create a useful pressure measuring instrument. So this is a bit of an ingenious way of attaching it to the mechanism, as the tube in this case is uncoiled. Well, I guess it's starting to coil. I would imagine, if you think of this like a balloon, if you blow air into it, it's going to, straighten out, and that's going to mechanically cause this little pinion gear in the middle to be moved by this actuating gear, and that moves a coil, which is attached to the pointer. You got a couple different looks at it here. Did I say pinion? Apparently here they're calling it a spur gear. And the other, it looks like about a quarter gear, eighth gear, is a sector gear. Whoops, sorry. Okay. Diaphragm it works similar. So with pressure, you can also use the diaphragm to measure. It's also kind of the same. If you can imagine, if this wafer was hollow, then you can blow air into it. It's going to move the center portion, the little platform in the center, which mechanically turns a sector gear, and that in effect eventually moves the pointer. They're talking this as an aneroid chamber. Well, let's see what. The diaphragm and bellows are two other basic sensing mechanisms employed in aircraft instruments for pressure measurements. And bellows would be a series of these, almost like a hand accordion. The diaphragm is a hollow, thin-walled metal disc, usually corrugated, When pressure is introduced through an opening on one end of the disc, the entire disc expands. By placing a linkage in contact against the other side of the disc, the movement of the pressurized diaphragm can be transferred to a pointer that registers the movement against the scale on the instrument face. The aneroid wafer, or the diaphragm, measures the difference in pressure between the vacuum inside the sealed chamber and the ambient pressure around it. Expansion and contraction of the pressure capsule or chamber mechanically moves the needle on a gauge. So it's a few different ways of saying the same thing. Here's a side view and a cutaway also. Here's the bellows that I was talking about, more like a little handheld accordion. You can imagine if there's a pressure change inside the chamber, inside the bellows, that it's going to move a somewhat complicated watch-like series of levers and pulleys and gears in order to move the needle on the instrument face. What is the aneroid? That's a sensitive component in an altimeter or barometer that measures the absolute pressure of the air. The aneroid is a sealed, flat capsule made of thin corrugated discs of metal soldered together and evacuated by pumping all of the air out of it. Evacuating the aneroid allows it to expand or collapse as the air pressure on the outside changes. Another view of the bellows. And like I said, it's when there's a number of diaphragm chambers connected together. The accordion-like assembly is very useful when measuring the difference between the two temperatures. As a matter of fact, if the pressure coming in one side is one pressure, and the pressure coming in the other side, the two entrances, it's depending on the higher pressure is going to push the mechanism, the mechanical portion. I guess in this case it's a steel rod, and that is connected to our sector gear and to the spur gear, and then directly to the needle. I don't see any coil attached to this one. Just as with the simple diaphragm, it is the movement of the side walls of the bellow assembly that correlates with changes in pressure and to which a pointer, linkage, and gearing is attached to inform the pilot. Another view is if you had let's imagine a rubber wall that's set at 0. So if we have two different pressures coming in on either side, it's going to push the indicator just by attaching it to this flexible wall. That way you don't even need the bellows. You just have a little flexible wall there. That's also a good way of looking at what is differential pressure. When there's no difference in the pressure between the two inputs, it would be in the middle at 0. Otherwise, you're going to get a reading one way or the other because there is a difference. Pressure switches are also being used. Well, pressure switches are used that operate on the basis of pressure. So if pressure goes beyond or below a certain level, you can actually attach mechanical devices to it so that it actually not only indicates moves a needle, but it also opens or closes a micro switch. Those switches are used to activate warning lights or to sequence system activities. Basically anything you want to switch to do. And, whenever you're measuring the differential pressure, I can't think of any examples where one of the inputs is not atmospheric pressure. You're always comparing it with what's, what is either outside the aircraft, or I suppose you could, there may be exceptions. I can't think of any off the top of my head, though. This illustration looks like it must be a pressure switch. Applications for you looking at pressure in your engine would be oil pressure. There's very high oil pressure or low oil pressure. Usually it's low oil pressure. It certainly indicates a inadequate oil supply or some blockage. But the reverse is also true. Your oil pressure cannot be too high. It's the most important instrument used by the pilot to perceive the health of an engine is the engine oil pressure gauge. And that's very similar in your vehicle also. I think you already know that. You don't want to run your engine low on oil. And in the oil, there's not an oil quantity gauge like a fuel gauge. It's basically a pressure gauge. Oil pressure is usually indicated in PSI, and you can see that right on the face of the instrument, pounds per square inch. The normal operating range is typically the green arc. On reciprocating and turbine engines, oil is used to lubricate and cool bearings surfaces where parts are rotating or sliding past each other at high speeds. That's the primary use of lubricating oil. A loss of pressurizing oil to these areas would rapidly cause excessive friction and over-temperature conditions, leading to catastrophic engine failure. Same with on your automobile. You certainly don't want it to happen to your own automobile. You certainly don't want it to have it work on one of the planes that you're getting paid to be a professional on. Fuel pressure is another indicator based on pressure, PSI also. There's some critical information to the pilot. Typically, fuel is pumped out of various fuel tanks on the aircraft for use by the engines. If you have various, but typically it is stating that. A malfunctioning fuel pump or a tank that has been emptied beyond the point at which there's sufficient fuel entering the pump to maintain desired output pressure is a condition that requires the pilot's immediate attention. So your fuel quantity indicator gauge isn't enough. The fuel pressure should also be monitored. And you can see there's a green arc and two red radial lines. Hydraulic pressure, there's hydraulic fluid on board. Usually there's a reservoir. They're commonly used to raise and lower landing gear, apply brakes, operate some flight controls, and more. Sufficient pressure is developed by the hydraulic pumps, and that's actually how you're going to raise your landing gear. If you don't have enough pressure, your landing gear are not going to be moved. They might be able to be lowered because of gravity and their weight, but once they're lowered, they're going to be lowered if you don't have hydraulic pressure. Hydraulic pressure gauges are often located in the cockpit and at or near the hydraulic system servicing point on the airframe. Remotely located indicators used by maintenance personnel are almost always the direct reading Borden tube type gauges. also PSI. A Borden tube instrument may be used to indicate what? The options are pressure, temperature, position. Well, let's just see what it can be used for. Well, we saw in the last presentation that it is used for temperature and pressure. What about position? I can't imagine how. I think of that mostly like position of the flaps, which that would not measure temperature or pressure. That's pure position. So it would just be 1 and 2. A. The operating mechanism of most hydraulic pressure gauges is it the Borden tube? B, an airtight diaphragm? C, an evacuated bellows? Now we're talking about hydraulic pressure. I think we just saw that the Borden tube is the most common. The airtight diaphragm, how are you gonna? You're not really going to use that to measure the pressure of a liquid. And same with the bellows, so it'd have to be the Borden tube. What else? Manifold pressure gauge. In reciprocating engine aircraft, the manifold pressure gauge indicates the pressure of the air in the engine's induction manifold. So that's the other main pressure gauge. So we looked at oil pressure, and we did look at fuel pressure a little bit. Manifold pressure, and that is the intake manifold. This is an indication of power being developed by the engine. The higher the pressure of the fuel-air mixture going into the engine, the more power it can produce. This gauge is also used it also uses a port for sensing pressure. An unobstructed static port would cause the gauge to read the current ambient atmospheric pressure with the engine off. Okay, so that's more of a differential pressure if there's a port. And if the port is reading the pressure from the outside, if you're not getting any type of engine induction pressure, it's just going to read what the atmospheric pressure is outside. What does a reciprocating engine manifold pressure gauge indicate when the engine is not operating? I guess I just answered it too quick. Is it zero pressure, differential, or existing atmospheric pressure? Well, the engine's not on, so you're not going to get any special reading inside your intake manifold other than just the prevailing atmospheric pressure is C. Zero pressure, it'd be in outer space. Oral question. A static check may be performed on a manifold pressure gauge by using what piece of information? How can you quickly check whether or not your manifold pressure gauge is accurate? Well, mostly by reading it to see whether or not whether it's reading approximately what the temperature is outside right now. So the current atmospheric pressure, that's the piece of information you'd need. fuel. Let's do this real quick. I'm starting to run up to break time. Apparently, some of this is covered under your aircraft fuel systems. They do talk about the indicator gauges. But there's a question or two that will pop up here under aircraft instruments, an FAA question or two, or a oral question. So let's take a look, or it's going to be a review if you've already done fuel systems. There's several types. One's the mechanical. You can see there's no power attached. Basically, you have a little floater inside your fuel cell or tank, and as that moves, that actually will change what appears on the face. That's nearly a direct connection. There's a magnetic coupler that will dampen the sloshing of the fuel, which reduces gauge. Otherwise, you'd have it moving quite a bit, especially with the fuel sloshing all over. That's mechanical. There's also electrical, and here we see the difference of the resistance of A and B, and there's a tank resistor, which in effect is going to increase the resistance of the B leg of this electrical circuit, so it's going to have an impact on the magnetically driven needle in the indicator. But you still have a mechanical device that's attached to the variable resistor for the tank, and that's some item that's floating in the fuel cell. There's capacitance types, using the principles of capacitors, where they're actually using it to measure how much is there air compared to fuel in the area between the two plates. And air, I think, is like a dielectric of 1, and fuel is a dielectric of 2. So basically, if there's if there's half air and half fuel, you're going to get a dielectric of what, 1.5, and that can be used on a gauge. Compensator, it's built into the system in order to adjust the indication for temperature changes. I don't think you deal with that too much, but there may be a compensator attached to the capacitance type fuel quantity indicator gauge. What quantity is accurately measured by a capacitance type fuel quantity indicating system? Now I remember this one. It was a little on the tricky side. What are they actually measuring? Well, they're trying to measure either the volume or the weight or the mass. The mass was the word, because volume isn't quite. There are differences in temperatures and it could impact the reading. So I think it actually reads the mass of the fuel. Yes. A flow meter measures the amount of a fluid passing a given point by measuring the revolutions of a calibrated vane. So if the fuel is moving, it's going to spin the vane. So it measures the flow. You could think of that as putting a little something, a little star spinner in the river, and you can see that the river can turn the device. If you actually put a little counter on it, you can measure the flow of the river. In effect, you can, better yet, devise an instrument to do this, and that would be a contained instrument that has the fluid passes and moves these impellers and discs or turbines, and that can be electrically attached to an indicator by wires. So it doesn't have to be, it could be in the cockpit, where it would be flight deck, and transmitter would be in a fuel line somewhere. The amount of the turbine is displaced depends on the quantity and viscosity of the fuel that is spun towards it. Yeah, thicker fuel, I guess, is going to move those vanes a little more aggressively. Or the impeller, the little turbine, which I guess it is vanes. Fuel flow transmitters are designed to transmit data. Is it mechanically, electrically, or utilizing fluid power? They transmit the data with the wires. We did see that there are two different components and connected by the wires, so electrically should be the correct answer. Okay. I don't know. 51 minutes. I guess we're going to go into break time. I think I'm going to save synchro. It's got to be our last position. We're going on. A synchro system basically is another way of showing the indicator needle here is being actually driven by magnetic forces. And you can see that wires come into three different parts of the donut shaped iron core. The shortened word for the word synchronous. And basically, if you can do this, you can get this to copy through the wires onto another unit. Or in this case, it'd be that whatever that other side is reading is going to appear on this side. They're used as remote position indicators for landing gear, autopilot, radar, and many other remote indicating applications. Flap position, and fluid pressure indicators also have synchro systems. Synchro transmitters connected to a synchro receiver. It's going to be by wires electrically. Describe the basic operating concept of a synchro type remote indicating system. I'm just going to go ahead and put that up and see what the recommended language to answer that is. It's just one sentence. A remote transmitter electrically signals a receiver inside the instrument. Here's another look at the angle of attack indicating system. This is something else you may have already seen in position and warning. I guess we're jumping to the question. The operation of an angle of attack indicating system is based on detection of differential pressure at a point where the airstream flows in a direction. Is it not parallel to the true angle of attack, or parallel to the angle of attack, or parallel to the longitudinal axis? Did we kind of skip over here? It's the angle of attack. It senses the angle of attack the aircraft is flying by the pressure differential inside the paddle chamber. So the paddles are actually being moved based on the airflow. So I guess the not parallel is going to be the difference. What's parallel with the AOA of the aircraft? And basically, if you're not parallel, if you're not running to the same direction, you're going to get an indication in the instrument. All right, there we go. All right, thanks for bearing with me a little bit longer, and I'll see you on the next one. All right, thanks again. Goodbye.